Okay. Now back to this very important properties of power line. So that means when you have two, number one, when you have two power lines and a transversal, this angle, let's call that X, and this angle is called Y. And they add together has to be 180. Now, in geometry, we just call them, those two angles are supplementary. Just means to add together 180. Now, this is very important because the other properties we can uh, deduce based on this property. Okay, so the second one said if two parallels are caught by lines by caught by transversal, this is our this line. That's our transversal. And the corresponding angles are congruent. The corresponding angles means one angle is inside the two line, the other is outside. So the Z here, this angle here is the corresponding angle. Now, property 2 tells us Y is equal to Z. Well, how do we prove that? So we're going to based on our property 1 that X plus Y is 180. Now you can see X and Z, when you add together, also be 180 because it's on the same line. So X plus Z is 180. Now we also know that X plus Y is 180. So therefore, uh, if we use top to minus the bottom, so X cancel, Z minus Y is 180 minus 180 is 0. So therefore, Z has equal to Y. And it makes sense because X plus Z is 180, X plus Y 180. So Z and X has to be the same. So therefore, this is our second property that the corresponding angles are congruent. Good? All right. And then we're looking at number 3. Again, our first property is the most fundamental. Once we understand the first one, then the rest we can easily prove it. Okay, so number 3 says in two power lines, if two power lines are cut by a transversal and um, the alternate interior angles are congruent. The alternate interior angles, that means they are on either side of the two lines. So there's a, remember there are vocabulary. This is called alternate interior. Interior angle means the angle between these two lines. Angle outside those two lines, like Z, that's called exterior angle. Now, if it's on the same side of the line, this is what we call same side interior angle. But sometimes we call that consecutive interior angle. But if he's on the other side of the line, we call that alternate. So that means this will be alternate. Let's call this one A. And this property told us that A is equal to Y. Again, we're going to use this property here. And we know that X plus Y is 180. And we can see that also X plus A is 180 because it's on the same line. So A plus X is 180. And also we know Y plus X is 180. So therefore, A has equal to Y. And you can see that as long as this is uh, true, then the number 2 and number 3 are both true. Good? All right. Okay. So then we're looking at the property of parallelogram. What we learned early on is that, first of all, the definition of parallelogram is that the two sides are parallel. So this side parallel to this side parallel to that. So the So the two pairs, they are parallel to each other, and that's why we call it parallelogram. And we have this property is that for the parallelogram, the corresponding sides of parallelogram are congruent. That means this side, let's call this A, B, C, D. Then AD is equal to VC. And also the top, AB here, is equal to DC. So that's the first one. Second one is corresponding angles of a parallelogram are congruent. That means this angle is congruent to this angle. And this is only true when they are parallelogram. And this angle is congruent to this angle. So that's our number two. And number three says that the diagonals of parallelogram bisect each other. So if you have a diagonal, one is go here, and another one is going here. So they bisect each other. That means this side is congruent to this side, and this side is congruent to this side. Okay, are we good? Very good. And then we talk about some special parallelograms. So we know rectangle uh, is a special parallelogram, or rectangles are special parallelograms. A square, um, a special case of rectangles. So of course, that's a special case of parallelogram. Also rhombus. And so you got parallelogram like this. Then this is parallelogram, and square is also parallelogram. Also, we have something called rhombus, that four sides are the same, but the angle is not 90. So you can see that this this one is a special case of parallelogram, and this one is a special case of parallelogram, and the square is a special case of a rectangle. It's also a special case of a rhombus. Good? Okay, perfect. So now we're going to looking at learning something new. So theorem 2-6-1. It says that if two lines are parallel, then the distance from all points on the one line to the other are equal. So it's kind of like you think about a railroad track, and the things between them, they have to be equal. And the reason for that is the distance is defined as the shortest uh, line that connect two points. So the shortest will be perpendicular to this line. So it'll be 90 degree here, 90 degree here, 90 degree and 90 degree. Now you can see this is a rectangle. And a rectangle, therefore, rectangle is a special kind of parallelogram. And we know one of the properties of parallelogram is the corresponding sides are congruent. So therefore, AC is equal to BD. So that means no matter where you find the distance between the two, they're always congruent, always the same length. Good? Yeah, very good. So now we're going to looking at the other problem here also. We are going to kind of we're doing some practice on how to prove things. Okay. Um, this uh, this theorem says that if three lines divide one transversal into congruent segment, then they also divide any transversal into congruent segment. So what that means is that we have this line the graph here. And we have three lines parallel. This, and this. And this line is cut this side and this side equal. So that means AB equal to BC. Then therefore, XY has to be equal to YZ. So this is basically what this theorem says. So if three parallel lines divide one transversal, the one on the left is one transversal. So this line here is one transversal. And if it into congruent segment, that means AB is equal to BC. So BC, then it will cut another transversal. Those also will be congruent. It doesn't mean that this line is equal to this line. It means they are not. Sometimes special cases they do, but in general they are not. And you can see that pretty easily. If we draw another transversal, go like here, then from here to here, definitely bigger from here to here. So, but here it says that if this side is congruent to this side, then this side also congruent to that side. So that's what we got here. If AB equal to, so that's our if BC, then XY equal to YZ. Okay, now we're going to do some work here to prove it. That's the case. All right. So first of all, we know AB is equal to BC. We call that given. That's what's given in, and that's our condition. Then we're going to draw a line XD parallel to AB. So we draw a line here, goes through A, parallel to AB. Then we're going to draw Y, another line here. So this is XD, and this is XE, YE. And this one is parallel to that one. Well, what do we know? First of all, we know YD, XD sorry. We know XD is equal to AB, and DYE is equal to YE is equal to BC. Okay, so first of all, let me add this before that. Okay, so we add this line in there before that. XD is equal to AB, and YZ equal to BC. Now, why is that? What do you think? Hello, Mia? No problem. Well, see what we got. Now, if AB is parallel, well, we draw XD parallel to AB. So this side is parallel to this side. And we know this line, top line, is parallel to the middle line. So therefore, this side is parallel to this side. So therefore, what we got here is parallelogram. And remember the properties parallelogram is the corresponding sides are congruent. So that's what we're using. So that's how we know XD is equal to AB. Same thing here on the bottom here, we actually did the parallelogram. So therefore, corresponding sides are congruent. We got YE equal to BC. And now we know BC is equal to AB, that's given. So therefore, XD is equal to YE. Okay, so we got to this part. So let's see how does that help us? Yeah, so we got XD here and here, this YE here. Now we know this side is congruent to this side. And we're going to prove XY equal to YZ, but we got this part now. Okay, very good. Then we know the angle XDY, XDY is this angle, and this angle is congruent to YEZ. Actually, let's move that up a little bit. Maybe we can make that a bit bigger. Okay, just look at big. We got this is a D and this is a E. So we know this side is congruent to this side. And now we know that this angle is congruent to this angle. Yeah. Why is that? Yeah, think about the properties of power lines. So we know this line is parallel to this line. And this line is parallel to this line. Well, they are not vertical angles. And so because this, we're going to use on the property that this line is parallel to this line. So that means this angle is congruent to this angle. So x dy is congruent to y b d. And that's the corresponding angles. Um, so, and also this angle is congruent to this angle. So this is congruent to BCE. And remember, those lines are parallel lines. This line and this line parallel. So therefore, YBD, so this angle, and it's going to congruent to that angle. But we already know this angle is congruent to this angle, and this angle is congruent to this angle. So therefore, these two angles are congruent to each other. So we got this one. Good. All right. Okay. So can go back. What do we know so far? Yeah. And we know that this line is congruent to this line, and this angle is congruent to this angle. We just need to find one more angle. Okay. Well, one thing we know that this angle is congruent to that angle. Well, that is the corresponding angle between those two power lines. So what we got here, the triangle xdy is this triangle, is therefore congruent to this triangle. And why is that? What theorem do we use when looking at number 7? Well, they are congruent. Yep, very good. It's angle side congruency. Perfect. We got this angle, and the red angle, and red angle, and blue angle, two angles, and the side. Therefore, this line xy is equal to yz. And why is that? Yeah, remember we have a acronym for this one. Well, it's not that. This is something we called XY is a side of a triangle. YZ is a side of the triangle. Because it's two triangles congruent, then any part of the two triangles are congruent. So this is something we call CPCTC. And this is corresponding, the first one, C, corresponding parts of uh of actually not of congruent triangles. Congruent. So the second C is a congruent triangles. T is a triangle. Triangles. So corresponding part of congruent triangles are congruent. So the last C, congruent. So we write as, if we want to give a reason, we just say CP CTC. So congruent parts of corresponding parts of congruent triangles are congruent. So therefore, we prove that as long as AB is equal to BC, then XY has to equal to YZ. Okay? All right. So let's looking at the next theorem. This actually is pretty straightforward because we had the previous theorem. Theorem 2-6-3, a line pass through the middle of one side, this side, M, and is parallel to the other side. So it's parallel to this side. It will pass through the midpoint of the third side. So as long as M here, this is congruent to this, and this line, as long as it is parallel to the base here, then it will cut this line into two equal parts, this and this. Okay, so how do we prove that? So we're going to draw the line parallel to MN through point B. So we draw another line here. Well, now it looks like what we learned earlier. It's kind of like the one in before. We extend the BC and we draw the line parallel to MN. Now you can see we got three parallel lines. And we know this and this are given, but based on the previous, this is our Y, previous theorem. So theorem 2-6-2, then AN will equal to NC. So that's based on the previous theorem we did early on. So the last one is our conclusion here. N is the midpoint. Why is that? Well, N is definitely between A and C, but N could be here or here. So the reason for that is this is the reason for this is a definition of middle point. Good. Because the definition of middle point is that this side is equal to the other side. And we already proved that this side AN is equal to NC, so therefore N has to be a midpoint. And in geometry, we call this the definition, because the definition of middle point. So N meet that definition, so N is a middle point. Good? Perfect. Okay, so we got one more theorem to go. So theorem 2-6-4, the segment joining the middle points of two sides of triangle, first of all, is parallel to third side. B is half the length of third side. This one actually take a little bit of work to get to prove it. Okay, so first of all, we're going to draw a line parallel to BC from N to N prime, assuming that N is not parallel to BC. So we draw a line here, N prime. So N prime is parallel to BC. Well, then based on the previous theorem, we know that because this is the middle point, and this line is the power line. So based on the previous theorem, then n prime has to be the midpoint. And we already also we know n is the middle point. That's the given. So therefore n and n prime has to match. So basically they are on the same point. Okay, so that's how we got that done, is to prove that Mn, so therefore Mn is parallel to BC. Now, so that's the first part, Mn is parallel to BC. Now, once we have that, then we're going to use um, uh, um, triangle congruency to prove that Mn is half of BC. So the second part, the B. Okay. Our A is to prove that it's parallel to third side. Then B, we're trying to prove the half length of third side. Okay, so again, you can see when we prove something in geometry, we actually draw a lot of what we call construction lines. So we're going to draw a line from M to D so that, okay, we draw M to D. We got a line like that. And so that MD is parallel to NC. Okay, so now we know this is a parallelogram. So really based on the definition parallelogram, because we know this side and this side parallel, this side and that side parallel, so it's a parallelogram. Okay, so we got that. Now, according to the properties parallelogram, DC is congruent to MN. So remember that property, DC is congruent to MN. Yeah, so what is the property we're using here? Well, remember we learned that for parallelogram, the corresponding sides are congruent. Remember that? As long as a parallelogram, this side is congruent this side, and this side is congruent this side. Well, we already know that this is a parallelogram, so therefore, Mn going to congruent to each other. So Mn is equal to DC. And good. Yeah. Also, MD is equal to NC. So that's property of parallelogram. Okay. So now we looking at these two triangles we got here. One is the top one, AMN. Another one is the bottom one, M, this one. Okay. Well, we know this side is congruent to this side, and we know uh, this angle is congruent to this angle. Okay, that's because we got the power line. This power line, this power line. So these two angles are uh, corresponding angles. So they are congruent. So we got one side and the angle. So AM is equal to MB. And the angle AMN is congruent to angle MBD. Okay. So one side and the angle. We just either find another side or find another angle. Well, we know that this side is parallel to this side. Okay. So therefore, this angle and that angle are congruent. Again, this is because they are corresponding angles. So now we can prove these two triangles are congruent. And why is that? Think about triangle congruency theorem. Yeah, Mia. Well, it's not side, side, side. Remember, we got actually two angles. The blue angles are congruent, the red angles are congruent, and also the line between those two. So that's angle, side angle. Now, once we prove that, then we know uh, BD, this part, is equal to MN. So we got BD is equal to MN. And this is something we call CPCTC. Remember we did early on. Well, so if this is congruent to that, and also we know this side is congruent to that, so BD is equal to MD. We also know that DC, oh, sorry, equal to MN, not MD. Uh, so BD here equal to MN. And DC, we already know, proved early on, is MN. So therefore, DC is equal to BD. So that means this side is congruent to that side. So therefore, the MN then is half of BC. Yeah, because BC is BD plus DC, and both are MN. So therefore, BC is twice MN. If we divide by 2 on both sides, then MN is half the BC. Good? Okay, so now we're going to do some exercise, okay? Now, we have this triangle, uh, a triangle ABC. So is this triangle ABC. And we have some midpoint. D is midpoint, F is midpoint. So yeah, and the E is the midpoint. So D, F, E. We got A, B, C. So if AC is here, is 10, what's EF? So we know AC is from here to here is 10. And what is this side? What is EF? Yep, it's half of that. Remember, we learned early on. So this one, if this side is half of this side, this is the previous theorem we just proved. Very good. Okay, that's our A. Then our B is DF is equal to 7. DF is here. If DF is 7, what happened to AB? Yeah, again, D is the midpoint, F is the middle point, so we connect them like that. And what's the relationship between DF and AB? Right, AB is twice of that, is 14. Okay, now we're looking at C, CF. CF is, where's CF? CF is here. Now, is CF is 8. What happened to DE? This line. Well, you can see that DE is also a middle point. D and E are middle point. And also F is a middle point. Right. Yeah, because DB is half of CB and CF is also half of the CB, so they are equal. Very good. Let's do our last one. If AB is equal to K, this is AB is K, we call them K. What happened to DF? What is DF equal to? Yeah, very good. That's what it is. Okay, good job. That's all we have for today. Okay. And I'll send out the homework and I'll see you next week. Okay.
Bye.
Bye. Take care.
Thank you.
You're welcome.